Hello, hello, hello world. Cool. To one side and put it in alphabetical order. So if I bring everything to the left side, I'm going to have a times x minus x0 plus b times y minus y0 equals 0, right? Where x and y0 is some point on the line, any point on the line. So this is just another way we can write the equation for a line that we've probably never seen before in most books, but it turns out it's going to have a relevant geometric interpretation. So just note here that this A right here is the same as the vector A. Ooh, I don't like that gray highlighter. I hit a wrong button last time. And the B is the same B as above from the normal vector. So we have this relationship between the values of the normal vector and these multiples and the slope. With me? All right. So why would we bother writing something in that form? Well, it's helpful when we move on to 3 dimensions. So this is a 2-dimensional line in a normal vector. Okay. What happens if we generalize this out to 3 dimensions? Well, then we would get something that looks like this. New page. We would have an A times x minus x0 plus a b times y minus y0. And if we have a 3rd dimension, oops, we would have a plus, let's call it c. That's a c times z minus z0. And that's equal to 0. And what do all these numbers mean? Well, the point x0, y0, z0 is a point on this object. Point on. And the vector A, B, C is a normal vector to whatever I'm sitting on in 3 dimensions. Okay. Question is, if I graph that black thing, what is it? So we're just going to look at a simple version of that. Suppose I let the normal vector be 1, 1, 1, 1. And I let the point be a point at the origin. So we'll get something passing through the origin. What's it going to look like when we graph x plus y plus z equals 0? What am I going to generate? Anyone want to take a guess? I think there's 2 good guesses here. A line is one guess. What's the other guess? What's that? A box, that's another good guess. Anybody else? Okay, let's take a look. Let's ask GeoGebra. What does it look like? So just a note on this, if you think about slope-wise kind of stuff, we have slope going in 3 directions here, which is why vectors are important when we move to 3D. 2D, real easy. 3D, that extra direction makes things way more complicated. We can move in many directions. Let's see, GeoGebra. All right. So x plus y, plus z, equals 0. What is it? Let's rotate and see. Oh, it's a plane. Okay, so the way to think about it is, if you have a square in a 2-dimensional thing, what's the next version up of a plane? A square, sorry, it would be a cube, right? So similar thing happens with equations when you move in 2D with a line. If you project a line into 3 dimensions, you really have a plane. It's 1 dimension lower than where you're sitting in. If you want to graph a line in 3D, that's actually way more complicated than graphing a plane. To graph a line, you have to use parametric equations. Okay. To graph a plane is in 3D is like a line in 2D. It's not much more complicated. So to graph a plane, well, there's a lot of ways to think about it. If 2 points make a line, how many points make a plane? 3 points will make a plane. If you have a 4th point, maybe it's in the same plane, maybe it's not. Do you ever have, like, how many legs does a table usually have? How many tables don't wobble? Not many. Most tables wobble. And the reason is any 3 legs will always make a plane. If that 4th leg is not perfectly on, you don't have a plane, right? And think about it. If you're at a table with people and you lean on one side and then you get away, the table might wobble, okay? So when you're leaning on it, it is then stable on 3 of those legs. So that's why a 3-legged table is always a better thing than a 4-legged table, because a 3-legged table will not wobble. When you start adding more legs, then it's more complicated to find the right plane, which is kind of crazy. All right, so just some notes on planes, and then we'll actually calculate a plane. 3 with an extra T, one of them silent. 3 points make a plane. Not any 3 points though. What do you think has to be special about the 3 points? No, not same angles. They just can't line up, because if they line up, well, then you have a line, and there's lots of planes that go through a line. Okay, so 3 points make a plane if the points aren't collinear. Collinear meaning on the same line. Points are not collinear. If I have 3 points, I have a plane, and if I have 3 points, I can also, based on those 3 points, make a pair of vectors. I can make multiple pairs of vectors. I'm just going to pick one pair. And we talked about this the other day in class, that if I do have a pair of vectors in 3 space, I do have a plane running through those vectors. Okay, and the cross product helps us find the normal vector to those. So 2 vectors make a plane, and we still have the same catch if the vectors aren't collinear. And then the other magic thing we have on our side with planes is we have this general formula for a plane. So I'm going to call it the standard form for a plane. So standard form is that A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0 equals 0. So all I need is a normal vector and an initial point, and then I have the plane. So we're going to give this a shot. I'm going to pick 3 points in the plane, and we're going to see if we can calculate the equation for the plane based on the information we just looked at. So back to GeoGebra. Let's get rid of you and pick some points. How about, hello, why won't you type? Uh-oh, I broke GeoGebra. Turn it. Leave and come back. All right, there you go. So let's see. Let's pick some relatively simple points. So how about, oop, I already have those. 3 for X, 0 for Y, 0 for Z. That'll make things rather simple. And then let's go with, how about 1 for Y, 4 for X, and 0 for Z. And one more point. How about 1, 1, 1? All right, so then we'll rotate you this way. Okay, so there's my 3 points in space. And we're going to try to find the plane running through those points, okay? So to do so, we need to come up with some vectors, because we're going to use the idea of finding a normal vector to get the ABC, and then any one of those points could be our point on the plane. So let's generate some vectors. Back to my notebook. So we have the points 3, 0, 0. We have the point 1, 1, 1. And we actually, I should put them in the same order I wrote them before, like A, B, C. What was this one? This one was 1, 4, 0. Is that right? And then this one was 1, 1, 1. So what should be the central point of our vectors heading out? How about the 1, 1, 1? We'll have that be our central point. So let's say here's the 1, 1, 1. That's point C. And then over here we have point, let's see, this would be point A, and this would be point B over here. And so we're going to find these vectors right there as vectors in our plane, and then we'll calculate the normal vector coming out of C such that that normal vector is at a right angle to that and is at a right angle to that. That looks weird. All right, so that means I have to take A minus C to get this vector. This is, again, vector A, vector B, vector C. And so let's call our first vector CA. So A minus C is going to be 3 minus 1, which is 2, comma, negative 1, negative 1, 0 minus 1, 0 minus 1. And then we want the vector from C to B, which would be to take vector B and subtract vector C. 1 minus 1 is 0, 4 minus 1 is 3, 0 minus 1 is negative 1. Is my arithmetic okay? All right, and then let's see. If I think about the right-hand rule, if I say this is my, CA is my first vector and CB is my second vector, then my normal vector should be heading up out from that central point C. Does that look right? Yeah, I think that's right. Yeah, the whole right-hand rule always messed me up because I could never keep my right and my left straight anyway. All right, so then now we're thinking about, I like to think about the calculate, we need the cross product of these guys. So we need to find what is vector CA cross vector CB, because that will give us the normal vector or a normal vector to these two. So I have these stacked in the right order, thinking about, I like to use the matrix version to do it. So then I would think about my I, J, K up in the top row. So then imagine that this whole thing is a matrix. And I find that's the easiest way for me to calculate the cross product. So for calculating the I component, I cross out the i's row and column, and then I do the cross multiplication, subtraction. So -1 times -1 is 1, minus -3 is 4. So my first component is 4. I'm going to put it in regular vector notation instead of the IJK notation. All right, then we switch over to J. And if I wipe out the J row and column, then I have 2 times -1, -2, minus 0, that's nice, is -2 for J. Correct me if I mess up any arithmetic. And then crossing out the K stuff, 2 times 3 is 6, minus 0 is still 6. And that color is very hard to read. Let's make it black. So this should be a normal vector. Okay. So according to the theory, in order to turn the normal vector into a plane through these other vectors or points, I have to use the A, B, and C and then pick an initial point. I'm going to pick C as my initial point. It's kind of nice and easy. So my plane, I'm going to sneak it in under here, should have the equation A is 4 times x minus 1 minus b 2, or plus b, which is minus 2, times y minus 1 plus 6, my c, times z minus 1, and that should be equal to 0. So if I did this right, that plane should pass through my points, and this vector should be perpendicular to that plane. Okay. Now we calculated the plane to be perpendicular through C, but if I just give GeoGebra that vector, it will always put it at the origin. But GeoGebra has a nice tool for putting a vector anywhere you want. So I'll do that too in just a sec. All right, so let's test this. So back to GeoGebra. So the next, let's just plot the plane. Aren't you dying to see if it actually goes through those points? Did we do it right? So 4 times x minus 1 minus 2 times y minus 1 plus 6 times z minus 1 should equal 0. And we missed. Oh, man. It should be a plus 2, not minus 2? Let's go see the notes here. Oh my gosh, you're right. It's negative j. Yeah, that is a plus 2. Oh, nice job. Way to go. Yep, yeah. So I forgot, when you're calculating these guys, it's positive I vector, negative j vector, positive k vector. You have to alternate signs, which makes that 2 a plus. And that's the wrong magic pen. I don't know where to go to fix this. All right, how about over here? There we go. So that's a plus 2, and let's fix GeoGebra. A plus 2, will it let me correct it today? Yep, I think. Here. Yeah, look at that. We have a plane through those points. I think we did it, right? That looks pretty good, doesn't it? All right, let's see what the normal vector looks like. Okay, so when I first graphed the normal vector, 4, 2, 6, is that right? It's going to come, oh, I can't do a vector that way, right? I have to type vector, and then points, 4, 2, 6. Okay, there's the vector. It's coming out of the origin, so, but it's shooting through our plane. Does it look like it might be perpendicular to our plane? That looks pretty good. If we wanted it to pop out of one of the points, GeoGebra has a tool for that somewhere. So let's see, where is that tool? Vector from a point. So to make that work, what you do is GeoGebra is giving us instructions down here, hiding behind my Google Hangouts tab. I think it says click a point to have the vector go through. So let's say we want to go through point C. Oh, no, I want C. I guess I'll have to take B. So did I get B? And then click on the vector you want to come out of that point. Okay, there you go. Oh, and then I have to switch back to the move tool. and then I can rotate it. So now I have a point coming out of B, and that one should look perpendicular. I wanted it to come out of C, but I couldn't see C at the time. Okay, so there it is coming out of C. Oops, turn that tool off. And you got to remember to switch tools in GeoGebra. Yeah, so we have a whole bunch of vectors perpendicular to, or parallel to each other, perpendicular to my plane here. Fun, huh? Woohoo. All right. So forgot it does that. That's trippy. All right. Okay, let me stop there. The other thing I was going to do, and I'm running out of time, so I'll just have to show you. Am I logged in? Yep. How do I go to my stuff? Open. Parallelepiped. All right. Last night I built, no, I don't want to change your name. I just want to see you. View. I built a parallelepiped using that whole vector through a point thing. And I talked about this in class the other day, but we didn't get to calculate one next. What I started with is a pair of vectors in the plane, in a plane. Let's see, which ones did I start with? Where's A, B, and C? Okay, so there's A at the bottom. There's B. Okay, so I think I started with this vector right here in the base, this vector down here in the base, so that made my parallelogram for a base, and then I took this vector up to C there, and I used that as my third vector. And let me just take a snapshot of this and just remind you of what I can do with that. Control X, no, Control X, there you go. So we've got the theory we went over the other day that says if you have two base vectors, and so I'm going to say vector A, actually let's use a lowercase. Vector A is in the base, and I cross that with vector B, my other base vector. So those are my vectors down below. I have this one and say that one right there. If I do the cross product, the magnitude of that cross product is going to give me the area of this parallelogram. Okay. If I just calculate the cross product of A and B, that also gives me a normal vector to that plane right here. So the cross product without magnitude is a normal vector to the plane. If I do the magnitude of that, I get the area, which is kind of, I get two cool things out of it at once. If I then take a third vector, not in that plane, coming from one of the points in the plane, then I can generate a three-dimensional object called a parallelepiped. So let's say I come out like that with vector C. And so from each of these points, I have some similar vector coming out like that. And so I make this three-dimensional squished box thing. Anybody remember the cool name for this three-dimensional squished box? Parallelepiped. Yeah, so this squished box is called a parallelepiped, which I thought is just the coolest name ever. And then the cool thing is, if you think about the normal vector, so maybe the normal vector to my plane is this right here. So maybe that's n, my normal vector right there. If I dot the cross product, the normal vector, with my vector C here, what I'm going to get is a projection onto C, right? Dot product helps us get that projection, which basically gives me the height of my parallelepiped if that is the base. And so what I mentioned the other day is if we take that vector C and we dot it with the normal vector of A and B, which is A cross B, oops, and then we take the magnitude of all of that, then I get the volume, which is wicked cool. I get the volume of the parallelepiped. So the dot and the cross product together give us a vertical height we can measure from, because bottom line, in order to do areas and volumes, don't you need a bunch of perpendicular measurements? Yeah, and so that's what that normal vector does. It gives us a perpendicular measurement to work with. The dot product helps project the height onto that perpendicular line. And so normal vector to the plane dotted with the vector that makes the tall side of the plane gives you the volume of the plane all the time, which is kind of nice. So let's see, how many points do you need to make a parallelepiped? If a plane you need 3 points to make, parallelepiped is kind of like one dimension more complicated. So I would need 1, 2, 3, 4 points. Once I have those 4 points, I just have a whole bunch of parallel lines and planes based on those, and that generates the parallelepiped. So 4 points, or highlighting, 2 vectors make the base, and a third vector makes the rest of the 3D part of the parallelepiped. Say that 5 times fast, coming out of that. So we better stop here. We're out of time officially. Tomorrow is going to be a review day. Let's see, let me